you'll hear the term sampling resolution used. That relates to how precisely we need to make measurements. If, for example, we were to consider a temperature measurement, you can understand that how precisely we need to make the measurement depends on what we're trying to achieve with it. So for the sake of argument, if I just want to document the temperature for the weather, then it's probably enough to write the numbers down to the nearest degree, 24 or 25 degrees centigrade, probably doesn't matter. If I'm recording the temperature of a patient, then 1 degree centigrade intervals probably isn't precise enough. So the difference between 38 and 39 or 40 degrees is quite significant in clinical terms, and so I might choose to write the numbers down to 1 decimal place. You'll appreciate then that in order to set the sampling resolution for one of your physiological signals, you need to understand what you're going to use that measurement for. If you can understand the smallest change of your physiological signal that is of clinical importance, there's a rule of thumb called the rule of 10, which says something along the lines of your measurement resolution should be 10 times better than that. So for the sake of argument, if a 1 degree centigrade change in temperature is the smallest change that you would consider to be clinically significant, then your sampling resolution ought to be about 0.1 of a degree C. In a moment, we're going to study the effect of sampling resolution on some real waveforms. In order to do that, we'll be using a setup that will also appear in some of the other experiments and some of the other lectures, so it's worth saying a little bit about it. The sound card that I showed you a moment ago is connected into the computer, and in a few seconds we'll see the waveforms on the screen. At the moment, the input to the sound card is connected to the same signal generator that we were using in our earlier experiments with the instrumentation. In a later lecture though, that's going to change. On the left side of the screen, you can see the signal going to the input of the analog to digital converter. At the moment, it's a sine wave coming from the signal generator. On the right side of the screen is the signal after it's undergone digital signal processing. At the moment, there is no processing being applied to the signal, and so the output looks exactly the same as the input. In a moment, I'm going to turn the audio volume up and then artificially reduce the sampling resolution of the output signal. You'll be able to see and hear the effect of an inadequate sampling resolution. You can see the output signal has taken on a stepped appearance, which is exactly the same effect as the rounding in the spreadsheet that we saw earlier. You'll also note by listening that while the original tone is still there, there's been an added harshness which is caused by that rounding effect. Well, that's very interesting, but now I'm going to swap the inputs and see what the effect of an inadequate sampling resolution is on a complex waveform. In a moment, I'm going to bring in the exact same inadequate sampling resolution. Listen to the effect it has on the music. you can see clearly the effect that the inadequate sampling resolution has on the waveform. In addition, you can clearly hear the effect, which sounds like noise on top of the music signal. In fact, the error between the true value of the signal and the sampled value, which has been rounded, is known as sampling or quantization noise.